Hello everyone. I'm here to present this paper done in collaboration with Mahdi, Ghorbani, and Amir Shaikhha from the University of Edinburgh and Tobias from the University of Cambridge. So as you might probably know, tensors are a bit everywhere, from classical quantum simulation, machine learning, probabilistic programming, to name a few. And as such, it's no surprise that we have plenty of tensors framework to support those needs. The way we see it, there are a bit two extremes on the spectrum right now. We have those dense tensor frameworks, assuming you're doing computations on each and every element of your tensors, completely densely. And as such, are super optimized for this assumption and get great memory behavior and parallelization opportunities. So many use cases actually face sparse tensors, where most of your tensor will be filled by zeros, and most of your computations will be adding and multiplying zeros, so wasted. So we developed specific data structures to accommodate those and only store those non-zero elements, and specific algorithms on top of them to scale to the actually needed amount of computations. But doing so, you lose a lot of those lower level performance benefits. So the way we see it on many of those mentioned fields, what we see is indeed sparse tensors, but in a very structured and predictable way. So we can specialize to this very known structure instead of paying a huge cost to accommodate any pattern. So we're focusing on that and hope to bring both benefits to those cases that allow it. To do so, we already had some previous work. We work with the structure encoding like that, where we encode the indices of the values we do need to consider at compile time. Here, a trivial example of a diagonal matrix where we have this x equals y constraints to say those are the only indices we need to watch out for. The rest are zeros. We call that the unique set. We have an inference engine on top of that to propagate this kind of information from operation inputs to outputs. For example, when you know you're multiplying a diagonal matrix with a strided matrix, you'll know your output will be a strided diagonal, right? And we have an engine able to propagate this kind of information across the program. To clarify, the system is able to encode way more complex structures. Here, an example of a 4D matrix. With a way more complex structure. The engine is also able to recover intrinsic structures from specific computations. Here we're multiplying a vector f by itself all over again. So we got a lot of redundant values that we can skip over. So the shape this takes is in a DSL, where we have an encoding here of two diagonal matrices in A and B. A definition of some matrix product, the classical one. The engine can infer the diagonal output structure and the fact that we need only one operation per element. It will generate some specialized code, and we get way faster than a dense alternative, generating one single loop for this element-wise product. So that's all fine, and we reproduce part of those benefits where we do only the computations that are needed. But that's where this paper starts, because there's a lot of work to be done still. We don't have any storage benefit. We still access completely naively densely stored matrices. Plus, yes, the lower level, while not polluted by interactions, is still very suboptimal. We get huge strides in our accesses, and that's not good, and there was no parallelization either. So that's what we're working on this article, by working on a specific storage pattern to solve the first issues and to add some slight parallelizations on top of those computations. So let's talk about this storage inference first. At this point, we're looking at already inferred computations with well-known structures on our matrices. So we have some formulas to describe the subset of elements we do want to store and manipulate on our computations. And what we want is a linear index to store those in a buffer. How to do that? So what we observe is that most of our constraints are affine, meaning those subsets are polyhedral, and in the polyhedral background, a well-known operation is the Parvin algorithm, enabling us to get formulas for the size of those subsets. So that's part of it, and we can get an intuition on how to get an indexing from that, looking at the good old normal multidimensional array linearization scheme, where for a simple matrix in row major scheme, we know that the ij element would be this ni plus j, right? And we can cut that in two pieces. There are the elements on the line before them, which just makes up a smaller rectangle where we see our ni, and the elements before on the same line, giving us our simple j. So we can apply the similar pattern to our wilder shape, and we'll look at the elements on the line before and the elements on the same line before separately, and then we can call our Bavinock algorithm to get simple formulas for each subset and sum them to get our index. So we get an indexing function enabling us to store uniquely all those elements in these subsets, skipping over all the elements that we inferred that are not needed. That's all great. And this index have similar properties to this multidimensional one, so we get to reuse a lot of know-how. Most importantly, we don't have to pay specific attentions to those loops. We can just plug it in the generated computation so far, and we directly get those benefits of storing only the elements we do need at runtime. The memory behavior is, of course, way better. We see here on the diagonal product, we're simply iterating over contiguous elements, helping with vectorization too. Similarly, given those indexable independence, we can simply parallelize with the same classic techniques. So here we figure there's no dependency on this loop. We just compute each element independently, so we can parallelize it trivially. Again, use this compression scheme in the exact same way. So this way we get all our benefits that we wanted. And yeah, I stayed specifically vague on the speedups because I'm happy to see a good speedup as the next one. But at this point, we reach an interesting stage to me where we can compare not against the naive tensor implementations, but on expert work on the concrete problems we represented this way. This complex matrix I showed in the beginning is the covariance matrix used in polynomial regression, and it's so structured that in practice nobody implements it with those naive tensor approaches. People manually implement a specific kernel for those cases to get decent performance for those. And now we can compare against that, expressing them in terms of those tensor and recovering this level of specialization through those techniques. That's on the left here, where we are twice as fast as a good manual implementation from a fellow researcher of ours that we compared. Yeah. Similarly, we are on par with the classic triangular matrix vector product as implemented by Blas from the very Intel implementation on an Intel CPU. So we're pretty proud of those results. Last benefit of this storage scheme is that we get to easily compress and decompress our tensors. That is, for a user not willing to go the extra mile and manually create those buffers in that compressed scheme, we can simply generate code iterating over those points and simply moving data from the naive representation to the compressed form, or vice versa. Meaning we can interface with users simply creating the tensors the classical way. This amortized pretty well in what we observed in this same complex polynomial regression case. It speeds up the computation so much that it's worth it in the first case. For some examples, there's some overheads to using this optional transparency automatic compression layer, but if you iterate a bit, it might be worth it too. And again, one might go the extra mile and interface manually. So as takeaways, I'm pretty excited about these lines of work. I think it's a cool way to reproduce a whole set of manual optimizations, still very much reserved to expert implementers so far. It can be used pretty transparently to higher level users. So I think it's a promising way to deliver performance more out of the box to many scientific computing users. I'm going to be working on this for at least the next couple of years on my PhD. So if you're excited to know more, please reach out. This is my email address. Of course, there's way more in the paper. I'm available for questions or discussions on more details. Thank you.
We have plenty of time for questions.
Yeah, that's very impressive speed ups, and I would really love to see it, and it's potentially relevant to some of the stuff I'm working on with Tensor Algebra. But I'm just guessing, is the code available anywhere in its current form?
We did not completely publish the artifacts, but I'm happy to discuss it. This iteration is in not very usable state, but I'm glad I could look at it with you, and I'm working on more exposable forms of it right now.
Sounds good.
So let's keep in touch.
I want to ask about this last bit about extending applicability. So
yeah.
Are there applications you're interested in that you're not really supporting at the moment, and what's your favorite one that you would like to really support better?
I'm excited to try it out on classical quantum simulation right now, which can be used it can be expressed as a lot of very structured matrix products, yeah. In a sense. It's a very simple extension so far. In this case, we just have to consider complex arithmetic. There are many fields that will use more than trivial classical tensor contractions, things like logarithms and exponentials on the elements. And so far, this inference engine was not able to do so. It was very hardly focused on zeros and simple products and sums. And I'm right now getting to generalize over that a bit.
Okay, so no support for complex numbers right now?
Not in this state,
okay.
But I'm already working on it if you want to know more.
As someone who's had to write many of the weird formulas for higher order symmetric matrices, this is greatly appreciated. But kind of question, how compatible is the storage or the storage restrictions with things that are say computing a tile of something, or want to produce a tile of a layout, or other kinds of producer consumer patterns you might see in code?
I'm not sure how specific of a case you have in mind, but basically it's just a one-to-one storage pattern, so it's usually as compatible. The question will be, does it behave as good as one would expect, performance-wise?
The key question is this: can I say, suppose I want a particular box of the output or some subset, can I then query for that subset in the layout? And
yeah,
is there some way I can make it so that will be linear or at a constraint?
Yeah, I'd say so. It's actually part of the inference engine. Sometimes you're only using a part of the output, so you want to avoid computing the intermediary results because you wanted them. So that's very much part of the idea.
But could I as an example, suppose I want some part to be really vectorized, so I want to compute a box. Could I make it so that box would be in a particular layout, linear, so that it would be accessed with a particular function for say some sub-box? Probably,
I'm not sure I see the specific, but there's a degree of freedom in the order in which we lay them out. There's lots of degree of freedoms there. We explored them with basic heuristics so far, in the more higher level order to maximize temporal locality. Yeah. Is that, yeah? Happy to chat more because I'm not sure I got all your questions.